Okay, so this is kind of like part 2 of the video review of module 6. So in the previous part, we kind of just went over the basics of setting up your indicator variables for your categorical predictor, as well as how we interpret the coefficients associated with the indicator variables. So far what we've looked at is what we call multiple regression models with additive effects, where we basically add the effect of each predictor into the model. Additive effects assume that each predictor's effect on the response does not depend on the values of the other predictors, right? So in this example, we'll say beta 1 represents, when x1 increases by 1, the mean response changes by beta 1, when we keep these values constant, right? It doesn't matter what specific value they are as long as we keep them constant. Now, interaction effects, though, allow the effect of one predictor on the response to depend on the actual value of the other predictor. So not only are we keeping them constant, it's no longer saying we're keeping them constant. It's that, well, for each specific value of the other predictor, the impact of this one predictor differs. So I did give this example in this PDF, and we'll just go over it again, So we're looking at sale prices of homes with two predictors, square footage, and whether the home is air conditioning or not. So x1 is going to be the quantitative predictor, and x2 is going to be a categorical predictor. And we're going to use an indicator variable where it's equal to 1 if the home is air conditioning and 0 if it does not have air conditioning. So if we fit a model of interaction, so if we kind of look at these parts, this looks like your usual model, and then interaction is this additional term where we basically multiply the predictors together. So when you have this term over here, this is an interaction term. So again, just as I said before, what you want to do next is then break down this equation into each of the categories. So with no air conditioning, I1 equals 0, so this term disappears. This term disappears, So your equation is just beta 0 plus beta 1 x1. With air conditioning, I1 equals to 1. So if we sub in I1 equals 1, this is the resulting equation you get. And what we realize is not only are the intercepts different, the slopes are different. And the slopes tell us, how much does the mean of y change as x1 increases by 1. So it tells us with no air conditioning, when x1 square footage increases by 1 unit, the mean sale price increases by beta 1, but for air conditioning, the mean sale price increases by a value given by beta 1 plus beta 3. So the effect of square footage on the home prices depends on whether the home has air conditioning or not. So this is what we mean, The effect of a predictor on the response depends on the value of the other predictor, in this case, whether it has air conditioning or not. So when you have an interaction with categorical variables, and this is actually the case with or without interaction, I always say it's always best to break down the regression equation here into each of the classes of your categorical variable, just so they can see the impact of each of these coefficients. Now, I introduced interaction with categorical variables because I think it's a little bit easier to visualize it. Interaction can also occur between quantitative predictors, So again, if the impact of one predictor on the response depends on the value of the other predictor. Now consider a student score on an exam with two predictors, amount of time spent in remedial class, x1, and student's current GPA, x2. If we think the impact of time spent in remedial classes on the exam score differs based on current GPA, an interaction between these predictors should be used. And in this case, it could make sense, You might say, well, if your GPA is really, really high, then you maybe don't really need the remedial class as much as those with lower GPAs. So maybe the equation looks like this, So the interaction x1 times x2. So again, how do we see what's happening? You'll have to then set, the value of one of the predictors, make that a constant value, and see how your equation works out. So if your GPA is 2.5, so I'm subbing in x2, x2 is GPA, subbing in x2 equals 2.5 into this equation, I will get this result over here. And if I sub in when GPA equals 4 into this equation over here, this is my resulting equation for people with GPA of 4 versus when people have GPA 2.5. So we can kind of see, extra time spent in remedial class is more beneficial for those with lower GPAs than those with GPA of 4, So the increase in the response is 2, for every additional hour spent in remedial classes, whereas the increase for students with a GPA of 4 is only 0.8. So this is indicative, of an interaction effect. The impact of time spent in remedial classes depends on the value of the other predictor, GPA, So this is how you would think of interaction. So if you have interaction between quantitative, I always suggest fixing separate values for one of the predictors, especially, so you probably will want to use values that you're interested in investigating, so they can kind of see how that impacts, right, the overall equation. If you kind of look at this on its own, it's kind of hard to see what's going on. There's this hierarchical principle. If the higher order terms are significant, so an interaction term is considered a higher order term because this is of order 2, whereas the terms x1, x2 are of order 1. So if your interaction terms are significant, you should always leave the lower order terms in the model, even if in your R output it tells you that these terms are insignificant. But if your interaction is significant, leave all of them in. A few practical issues to be aware of when using R. It's always crucial to check if R views your categorical predictors correctly, i.e. that it views the predictor as categorical. Sometimes, right, in some of the examples we've seen so far, the data set uses numeric codes for categorical variables, and so R will view them as quantitative. So you must declare these to be categorical and can use the factor function. If R already views the variable as categorical, you don't have to do anything. If the data uses dummy code, so dummy codes are 0, 1, so those are actually numeric, but if it's numeric with dummy codes, then you don't have to do anything because the LM function actually converts any categorical variables into dummy codes behind the scenes. Also check your reference class, right? And you can use the relevel function if needed to change the reference class if you so desire to do so.